Hey everybody. So in the last lecture we were talking about the different mathematical tools that we use in astronomy for solving problems, making our lives easier, preferably solving problems while making our lives easier. So we're going to put that together today with another set of tools that we have for plotting the night sky, for watching the night sky, and mapping it in a way that we can then analyze our map of where the stars appear to be, how they appear to move, so that we can figure out why. Figure out the why. Why do the stars appear to be where we see them and appear to move the way that we see them? So let's start with talking about the stars and other objects that you see in the constellations on the night sky. We saw this picture in the last video, right? Like I said, this is the night sky looking south from Arizona. And when you're looking for familiar objects, when you're trying to figure out what direction you're looking in the night sky, it's always good to find something familiar. So if you recognize those three bright stars and if you know, oh, okay, those are Orion's belt, and if this is Orion's belt, then this must be Orion. And if you know that to the left of Orion is Canis Major and to the right of Orion is Taurus, then you've pretty much got the whole southern sky mapped out for yourself. And if you want to know all the other little things, you're like, oh, okay, what's below Orion? And then if you don't know this off the top of your head, then you can look up, oh, okay, Lepus is right below that, and so on. What did I just do? I found a group of stars that I'm familiar with, like, say, Orion's belt, and I used that to figure out, oh, here's Orion, here's Canis Major, here's Taurus. What am I listing? Orion, Canis Major, Taurus. These are constellations. All right? And so you might think, like most people do, that a constellation is just a group of stars. It's a stick figure. It's like a stick figure in the sky made of stars. And that's not it, actually. A constellation is not just a group of stars. A constellation is a whole region in the sky. And let me show you what I mean by that. So, in order to map out the night sky, astronomers have basically taken the entire sky and drawn a bunch of lines, like these red lines here. And so they drew a bunch of lines that said, okay, this is the border of one constellation, right? This red line here is the border of the constellation Orion. Here's the border of the constellation Lepus. Here's the constellation of here's the borders of the constellation Canis Major. Here's Monoceros. So a constellation is not just a group of stars. A constellation is this whole region in the night sky, or in the daytime sky, for that matter, in the sky. And anything that is inside of this border is in this constellation. What does it matter? Who cares? Well, because if all you're doing is thinking that this stick figure is the constellation made of stars, then you're missing all the good stuff, right? If all you're doing is thinking a constellation is a group of stars, then you might be missing the planets, the sun, the moon, comets, asteroids, nebula, galaxies, all the even cooler stuff, all the stuff that is even more interesting than stars are. So that's why we say, right, a constellation is not just a group of stars. It is that entire demarcated region of the sky. And anything inside this border is in this case, Monoceros. And they're formalized. The night sky has been broken up into these 88 regions, these 88 constellations, and everywhere in the sky, every location in the sky is in one constellation or another. It's kind of like, you can kind of think about it like the 48 contiguous states of the United States, right? The lower 48 states are not, I mean, it's all one contiguous landmass, but it's broken up, we've drawn a bunch of borders and broken it up into 48 states. The whole sky is divided up into these 88 constellations. Astronomers have mapped the sky, they've drawn the lines, and they've agreed, okay, these are the names of the constellations and here are their borders. That way, any astronomer in the world, not even professional astronomers, anybody in the world can look at the sky, and if you know that there's a comet in the constellation Lepus, then we all know where to look. Right? Regardless of what language you speak, regardless of where in the world you live, if you look at a star chart, then it should say Lepus. It's formalized. We've kind of all agreed to it. These are the rules of the game we're going to play. Now, you notice this drawing here, like, the winter triangle. What is that? That's what's called an asterism, right? An asterism is a stick figure made of stars, right? It is a familiar pattern of bright stars. So if you thought that a constellation was a group of stars, that's not a constellation. That's an asterism. Orion's belt is an asterism. It's these 3 stars here. Or sometimes the 4th one is counted there too, right? So Orion's belt is an asterism. The winter triangle is these 3 bright stars, Procyon in Canis Minor, Sirius in Canis Major, and Betelgeuse in Orion. And why is it called the winter triangle? Well, because these 3 bright stars are up in the sky all winter long. And so if you're trying to figure out where you're looking, look for something familiar, right? If you go out at night and you just see a bunch of stars and you don't know what you're looking at, look for something familiar. Look for something bright that you recognize. And obviously these red lines are not actually on the night sky, so you can't see those, but you can see the bright stars. You can see the asterisms. So what I just did a minute ago, right? Look for something familiar. Here's Orion's belt. That's an asterism, right? And once you know something, once you've found one thing that you know, just like I did a minute ago, if this is Orion's belt, this must be the constellation Orion, this must be the constellation Canis Major, and so on. Asterisms are great because they're usually bright, so they're easy to find, but also asterisms are great because they're not formal, right? The names of the constellations and their borders are formalized. We've all agreed this region is quote-unquote Canis Major. Asterisms are not formal. People have made up all kinds of asterisms, and nobody's going to tell you they're wrong, right? Who says you have to call these stars Orion's belt? Nobody. Who says you have to call these 3 stars the winter triangle? Nobody. You can make up your own. People have made up different asterisms all over the world throughout history based on their language, their culture, their history. They're informal, and they're taught from one generation to the next. So just like I'm telling you, these 3 bright stars are the winter triangle, and you'll see them up all night, all winter long. And then if you tell your kids and they tell their kids, then it sort of becomes part of our shared astronomical culture. In the summer, up in the sky all summer long is the summer triangle. It's Deneb in the constellation Cygnus, Vega in the constellation Lyra, Altair in Aquila, and this big triangle of bright stars is up in the sky all summer long. Notice what I just said. Altair in Aquila, Deneb in Cygnus, Vega in Lyra, right? Lyra is the name of the constellation, and within the border of Lyra, Vega is the brightest star there, right? Deneb is a star inside the border of Cygnus, right? Anything within the border of Cygnus is in the constellation Cygnus. Some asterisms are within one constellation, right? Orion's belt is all within the constellation Orion. Some asterisms straddle multiple constellations. Who cares? They're all made up. It's fun. It's fun to just, sort of look at these stars and remember a pattern or use them to find what you're looking for. If I were looking for, let's say, Cygnus, right? If I'm up at night looking for Cygnus, what do I look for? Well, I look for this big T shape, right? Because this big T is, Deneb is bright, but all these other stars are pretty bright also. And so if Deneb is up, or if Cygnus is up, you're going to see all of these. What is this, 6 stars? Are these 6 stars the whole constellation Cygnus? No, right? Cygnus is the whole region. And everything, the bright stuff, the dim stuff, the big stuff, the small stuff, anything in the border of Cygnus is in the constellation Cygnus. This sort of T cross shape is an asterism. It's just, a familiar pattern of bright stars that if I'm looking for Cygnus, I would say, okay, look for this big T. There it is. I'm sure cultures all over the world have different names for this pattern of stars, and they're all right. They're all correct. It's all about using asterisms to help you find, take the bright things, the things you're familiar with, like asterisms, and use them to find other things that might be harder to find, fainter things. Right? Because most of the objects in the sky are the fainter things. The bright things are rare, and so if you can make a familiar pattern, the winter triangle is, here's Sirius, here's Betelgeuse, Procyon, the third star in the winter triangle, is up there somewhere. But if I know that there's an interesting looking galaxy in the middle of the winter triangle, well, then all I got to do is look for these 3 bright stars, say, oh, there's the winter triangle, point my telescope in the middle there, and I should hopefully find the thing that I'm looking for. Even if I couldn't find the faint galaxy from the beginning by itself, using those asterisms to help me narrow down where to look helps me immensely. And people have been doing this for millennia. What if you wanted a more specific place to point your telescope, right? What if you wanted a map that told you where you were looking more specifically, right? Constellations are, I'll go back to this one, right? Constellations are great because it's like, okay, this whole area is Orion. But if I told you to point your telescope at a specific star in Orion, you'd look and go, well, Orion is big. It's this big area. Where specifically should I be pointing my telescope? And that's where having maps that tell you where to point, where you're looking in the sky specifically, can help immensely. And there's a couple of main ways of mapping out the night sky. The first one is called the horizon coordinate system. And basically, if you're standing on the Earth, right, here you are, you're standing on the ground, and your horizon is out there, right? Your horizon is out there in front of you. The horizon is where the sky meets the ground, right? Out there in front of you, and below the horizon you can't see stars because the ground is in the way, right? You can only see the stars and constellations and all the other objects that are above your horizon. Those are the ones that are visible to you. So the horizon coordinate system is a map of the sky from your point of view, right? It's all about there you are, you're looking up in the sky over your head, where should you look? So the horizon coordinate system is very user-friendly because it's all about you. It's all about you're the astronomer, you're in your backyard or at the park or on the top of a mountain, wherever. Where should you look? And the horizon coordinate system maps the sky using 2 coordinates to pinpoint spots on the sky. First, the horizon coordinate system uses altitude. Altitude is a measure of how high above the horizon a star is. So, from your point of view, the horizon is out here. If an object is right on the horizon, it is at 0 degrees altitude. And as something gets higher and higher and higher in the sky, then it's going to higher and higher altitudes. So here it says, for example, this star is 60 degrees above the horizon, so that star is at 60 degrees altitude. All right, until you're looking up, up, up at the point straight up over your head. The point straight up over your head is called the zenith. So whenever you look straight up, you're looking at the zenith. And the zenith is 90 degrees above the horizon. So the point right up over your head is 90 degrees altitude. So the altitude of any object in the sky is going to be from 0 to 90. Okay, so altitude tells you how high up to look, basically. Right? Azimuth is, do I have it? I don't really have it spelled here. Okay, let me spell this out. Azimuth measures where around the horizon you should be looking, right? So azimuth tells you where around the horizon you should look. Altitude tells you how high up to look. And it works like this. Find due north on the horizon. Due north on the horizon is 0 degrees azimuth. And then azimuth increases as you look to your right, or as you look around the horizon clockwise. So due north is 0 degrees. And then you look around, and when you're looking due east, if you're looking due east, you've rotated 90 degrees away from north. So due east is, there it is, 90 degrees azimuth. Okay, keep on going. If you look due south, you've rotated through 180 degrees. So due south is 180 degrees azimuth. Keep on going, and due west is 270 degrees azimuth. And then if you come back to north, you've looked 360 degrees around the horizon. You've turned, well, if it's 360 degrees azimuth, is back at 0 degrees azimuth. So azimuth is you're taking the horizon, you're breaking it up into 360 degrees of azimuth. And that one number, azimuth, tells you specifically what direction to look. And altitude tells you how high above the horizon to look. So let's say, for example, you're looking at this star right here, right? There you are, you're standing right there, you're looking at that star right there. It is at 60 degrees altitude, and it's in the southeast, right? If you look at that star is above the southeastern horizon. And so if due east is 90 degrees azimuth and due south is 180 degrees azimuth, then that star right there at above that point on the horizon, that's at 135 degrees azimuth, and it's 60 degrees above the horizon, so it's at 60 degrees altitude. So if you're looking for that star, those two numbers, 60 degrees altitude, 135 degrees azimuth, that tells you exactly where to look in your sky above your horizon to find that star. Okay? So there you go, right? You're not just saying look north, look east, look up, look down. You're saying specifically where around to look and how high up to look. Okay. Now, there's a second way to map the sky. Why? Well, because in this map really only works for you, right? It's all about where the sky appears, or how the sky appears and where the stars appear to look from your point of view, above your horizon. What about the rest of the world? Well, if you're looking at the sky as viewed from everywhere on Earth, right? Here's the Earth, and if everybody on Earth is looking out at the sky all at the same time, then the sky looks like this spherical shell hovering above the Earth's surface, right? This is not the real sky, right? The real universe is vast and three-dimensional, and some stars are in the foreground and some stars are in the background. But But the optical illusion, the appearance is that all the stars and constellations and the sun, the moon, the planets, the galaxies, the nebula, everything looks like it's on this spherical shell hovering above the Earth's surface. This spherical shell of the sky is what we call the celestial sphere. So the celestial sphere is this map, it's this appearance of how the sky looks hovering above the whole Earth's surface. Right? Standing here on the Earth, you can only ever see half of the celestial sphere. The other half is down below your horizon. So the reason why we have a second map is so that you can map out the entire celestial sphere. The half you can see right now above the horizon, and the half that's below the horizon at any given time from any particular place on Earth. And if you watch the celestial sphere, what you notice is, well, what's actually happening is the Earth is spinning, right? The Earth is spinning this way. And so since the Earth is spinning that way, eastward, then if you're standing on the Earth looking up at the stars, then the celestial sphere appears to be spinning in the other direction. Right? The stars are not moving, but the appearance is that what it appears like is I'm standing still on the Earth's surface, and if I look up, the stars look like they're moving, spinning around the celestial pole. Right? The north celestial pole is the point on the sky right above the North Pole. The south celestial pole is the point on the sky right above the South Pole. The celestial equator is this big circle on the sky right above the Earth's equator. And that's how we map out the celestial sphere. And at this point, you know what? Why don't I jump over to Taurus? Because this is a much easier to understand if you can look at it three-dimensionally. So, okay, here's the Earth, right? Here's the Earth's North Pole. Here's the Earth's South Pole. Here's the Earth's equator. And here's the celestial sphere. So, imagine, right? The sky right above the Earth's equator, right? This great circle on the sky hovering above the Earth's equator is what we call the celestial equator. The North, oops, didn't mean to do that. Pardon me, sorry. Right, it's harder than it should be. Okay, sorry about that. The North Celestial Pole is the point right above the North Pole. If we look south, right, the South Celestial Pole is the point on the sky right above the Earth's South Pole. And so we're basically taking the Earth's map, right, the Earth's features, with an equator, a North Pole, a South Pole, and we're mapping that. We're projecting that onto the sky. And that's how we map out the whole celestial sphere in what's called the equatorial coordinate system. So why does it keep doing that? Okay. Okay. This mouse is tetchy. Okay. So the other coordinate system, the other way of mapping the sky, is with units called right ascension and declination. Okay? And it works like this. We've taken the whole celestial equator and we've broken it up into 24 hours of right ascension. So basically, if I rotate a little bit, all right, let's say there's a star right there. Okay? The right ascension, if I change the right ascension, I'm changing where that star is, east or west, around the celestial equator. So the celestial equator is broken up into 24 zones, 24 slices, called hours of right ascension. Okay? And then each of those hours is broken up into 60 minutes of right ascension, and so on. So right ascension uses the same units as time, right? Hours and minutes and seconds. If you're wanting to break each minute of right ascension up, you can break 1 minute of right ascension up into 60 seconds of right ascension. So right ascension uses the same units as time, but it's not a measure of time. Right ascension is a measure of position, where the star appears around the celestial equator, where it is east or west around the celestial sphere. Okay? So right ascension tells me where stars are east or west. Declination tells me where the stars are north or south, where the celestial equator is at 0 degrees declination. And then if I look north, if that star is north of the equator, then it's at 20 degrees declination, 30 degrees, 40 degrees, 50 degrees, right? North, 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 until, if I look far north enough, eventually I'm looking at the North Celestial Pole. I'm looking at the point on the sky right above the North Pole. And that's 90 degrees above the equator, or 90 degrees north of the equator, I should say. All right. Let's go back to the equator real quick, and I'll put in 0 for the declination. Okay. And now if I look south, then the declinations south of the equator become negative. So, negative 10, negative 20, negative 30, and so on, so on. South, 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 until I'm looking at the South Celestial Pole, the point in the sky right above the South Pole, at negative 90 degrees. Okay. Oh boy, if you're annoyed, think how I feel. The South Celestial Pole at 90 degrees declination. Okay. So, declination tells me where the star is north or south of the equator. Right, north or south. Right ascension tells me where the star is east or west around the equator. 0 degrees declination is the celestial equator. No, not 90. 0. There we go. All right. What's 0 hours right ascension? How did we pick 0 hours right ascension? Well, let's look at the ecliptic here. What is the ecliptic? The ecliptic is the path that the sun appears to take around the celestial sphere every year, right? Not because the sun is moving, but because the earth is moving around the sun. And so as the earth moves around the sun, we on earth are seeing the sun from different positions around the solar system. And therefore, the sun appears from our point of view to be in front of different stars, in front of different constellations over the course of the year. And the ecliptic is the path that the sun takes. Essentially, the ecliptic is the path that the sun takes going in front of these stars over the course of 1 year from the Earth's point of view. All right. And notice that the equator, so the ecliptic and the equator don't line up, right? Why? Is it because the sun is tilted? No, the Earth is tilted, right? The Earth's axis is tilted relative to the sun, but this whole map, this whole equatorial coordinate system is based on how things look from the Earth. So, yes, the Earth's axis is tilted with respect to the sun, and therefore the sun appears to be tilted with respect to the Earth. And when the sun is, I can do this, right? Over here, let's imagine this is the sun, right? When the sun is north of the equator, then the sun is going to be higher in the sky for those of us living in the southern hemisphere. And if the sun is higher in the sky from your point of view, it's summer, right? So when the sun is north of the equator, that's when the weather's going to be hotter. It's going to be more summer in the north. 6 months later, When the sun looks like it's down here, the sun is in the southern hemisphere. The sun is in the southern celestial hemisphere. And then that means the sun is going to look lower in the sky for those of us living in the northern hemisphere. And therefore it's going to be winter. If you live in the southern hemisphere, it's the other way around, right? If you live in the southern hemisphere and the sun is in the north, it's winter for you in the south. If you live in the southern hemisphere and the sun is down here, right? If you live here and the sun is there, then the sun is high over your head. And if the sun is high in the sky for you, it's southern summer. So the tilt of the ecliptic with respect to the Earth is what causes the seasons. And there are 2 days of the year. There are 2 days of the year where the sun is right on the celestial equator. Those are what are called the equinoxes. So the vernal equinox is the middle of spring, and the autumnal equinox is over here, which is the middle of autumn, the middle of fall. Right? And that, the vernal equinox, is where they decided to put 0 hours right ascension. So if I put 0 hours right ascension, 0 degrees declination, nope. There we go. That's where the sun is. So they had to figure out where to put 0 hours right ascension somewhere on the equator, and they decided, well, the sun is so bright and easy to see, we'll do it based on the sun. Right when the sun is on the equator, on the vernal equinox in the middle of spring, that's where we'll start 0 hours, and then we'll start counting looking east. So, it goes that way, all the way around. And then if you look around the sky all 24 hours, you've looked one full circle around. So 24 hours of right ascension is also 0. You're back at 0. Okay. Hopefully that made more sense than some PowerPoint slides. So, we've got these 2 maps, right? The equatorial coordinate system maps the whole celestial sphere. The horizon coordinate system maps half of the sky, the half that you can see above your horizon at any given moment. All right? And these 2 maps are happening at the same time, right? The equatorial coordinate system is fixed with respect to the stars, right? Because here's the Earth, which means this circle here, that's the celestial equator. The North Star is the star right next to the North Celestial Pole. It's right above the Earth's North Pole. The South Celestial Pole is the point on the sky right above the South Pole. There is no South Star. There's no bright star right next to the South Celestial Pole like there is a North Star. And so if you're here living in the Northern Hemisphere like we are, you're always going to see the North Star. The North Star is always up in your sky above the horizon. From here in Arizona, you can't see the South Celestial Pole because we're in the Northern Hemisphere, which means the South Celestial Pole is always down below our horizon. As the celestial sphere appears to rotate every day, remember, it's not really the celestial sphere that's rotating, it's Earth that's rotating, but we see it rotating in the opposite direction, right? So, for those of us standing on the Earth, the whole celestial sphere appears to rotate once a day, and therefore, these stars at high declinations, like star A here is close to the North Celestial Pole, which means it just goes around the sky, always above the horizon, once a day. All right, let me say that again. This star A goes around the celestial pole once a day, but it never crosses the horizon. So it's always up in the sky, all day long and all night long. Star B here is right on the celestial equator, which means it rises in the east, goes all the way across the sky, sets in the west, and then it goes down below the horizon for the other half of the day, and then it rises in the east the next day. All right? This is why we need both maps. A map for all the stars and a map for the ones above your horizon at any given time. Okay? Let's look at some questions here. Real quick. All right. What do you think? Is the horizon that you're seeing out here, is that a real physical boundary that's blocking your view, or is the horizon an imaginary plane that extends from you out to the stars? It's imaginary, right? Because if you try to walk toward the horizon, you can't walk up and touch the horizon like it's a real physical thing, right? The horizon is just an imaginary plane that goes from your feet out to the stars. Right? Wherever you are on Earth, the horizon is always out there in front of you, wrapping around you all 360 degrees. Right? You're the observer there, right? That's you. There you are. That's you, right? Can you see an object located below the horizon? Can you see this star down here? No, it's below the horizon. The Earth is in the way. Right? The horizon might be imaginary. Well, then why is it blocking your view? Why can't, if it's imaginary, why can't you see things that are below the horizon? Well, because it's the Earth that's blocking your view. The Earth is real. The horizon is imaginary. Is there a star here that is unobservable? Sure. Yeah. Star B, right? When it's down here at position 4, it's below the horizon. You can't see it. You can't see it until it comes up at position 1 later on at night. Right? When a star goes from below the horizon to above the horizon, do we call that rising or setting? It's rising, right? Notice the arrows here. Star A goes around like this. Star B goes around like this. All the stars in the sky are going the same direction every night. The whole celestial sphere is rotating in one direction. Why? Because they're not really moving. The stars aren't moving. It's the Earth that's spinning. And since the Earth only spins in one direction, then from our point of view, the stars are going to look like they're going over our heads in the other direction. Right? So when star B goes from below the horizon to above the horizon, it must be rising. And if star B rises over there, if that's where stars on the equator rise, then you know that way must be east. Right? If that's the North Star, if that's Polaris, if that's the North Star, then the point on the horizon right below the North Star, that way must be due north. If that's where stars rise, that must be due east. Looking over here, right, if you're looking at the horizon and your back is to the North Star, well then this way must be due south. And then over here, where stars go from above the horizon to below the horizon on the celestial equator, that's where star B is setting at position 3. That way must be due west. And now you've got everything you need to know to figure out things like azimuth, because if this is north, east, south, and west, then this must be 0 degrees azimuth, 90 degrees, 180, 270, and then all the way around to 360 degrees azimuth. All right. This is why we have two maps. Right? In the equatorial coordinate system, star B is always on the celestial equator, so it's always at 0 degrees declination. Right? And it's always at the same position, so it's always at the same right ascension also. the right ascension and declination of stars doesn't change. As the celestial sphere rotates, the equatorial coordinate system rotates with it, so that this, star A, star B, doesn't matter where it looks from your point of view, that star always has the same right ascension and declination. So the right ascension declination system is always the same for the stars. The horizon coordinate system is always the same for you, because wherever you're standing, your horizon is out here, and from your point of view, north is always this way, east is always that way, up is always that way. North is always the same at the same place for you, but as the Earth spins, the stars appear to wheel over your head, and that means that the altitude and the azimuth of these stars are constantly changing. Right? This is why we have these two maps. Right ascension and declination is always the same for the stars. Altitude and azimuth is always the same for you, and we need to be able to switch between these two maps in order to know what we're looking at. And if we want to find something specific, we'll know where to look. Right? All of that has to do with how the stars move all night long and all day long, not because the stars are actually moving, but because the Earth is spinning once a day. Okay? So that's one way the stars move, is over the course of one day, because the Earth rotates once a day. The Earth is doing a second motion, right? The Earth is orbiting around the sun. And so when the Earth is over here, what does that look like from the Earth's point of view? Well, when the Earth is over here, the sun appears to be in front of the stars of Scorpius. In other words, right, because remember, Scorpius is a constellation. Anything within the borders of Scorpius is in the constellation Scorpius. So right now, when the Earth is right there, if the sun is in front of the stars of Scorpius, then the sun is inside the constellation Scorpius. 6 months later, when the Earth is over here, then the sun hasn't moved, the stars haven't moved, but now the Earth is on this side of its orbit, and that means that from the Earth's point of view, the sun will be in the constellation Taurus. So let's say, the Earth is right here in mid-November. So in mid-November, the sun is in Scorpius. And then the Earth goes all the way around the sun, and therefore the sun appears to go all the way around the ecliptic one time, and 1 year later, the Earth comes back here, it's mid-November again, and the sun is back in Scorpius. The sun is always in Scorpius in mid-November. Right? 6 months later, 6 months later it's May, right? Every May, the sun is in Taurus. And 1 year later, the Earth comes back over here, and the sun, there it is again in Taurus, right? The sun is always in the same constellation on the same day of the year every year. Not because the sun is actually moving, not because the stars are moving, but because after 1 year, the Earth goes around the sun one time and comes back to where it starts. Right? And that observation, the observation that the sun is always in the same constellation on the same day of the year, that's actually the basis for Western astrology. Right? Our sort of probably the astrological system that you're familiar with, sort of the Western system of astrology, was created 2,000 years ago when astronomers realized, what a weird coincidence. What a weird coincidence that on the same day of the year, the sun is always in the same constellation. And a year later, there it is again in the same constellation. What a crazy coincidence. Well, today we know, no, of course it's not a coincidence. But they thought that there was something deep and magical about that. That every year in Mid-May, the sun is in Taurus. Every June, the sun is in every mid-June, the sun is in Gemini, right? What an amazing magical coincidence. I wonder what else we can figure out, right? This must have seemed like fortune telling, right? This must have seemed like you can predict the future, right? You could predict that every mid-November, the sun will come back in Scorpius, and it'll happen the next year, and the next year, and the next year, right? And so this is how astrology got to be a system of fortune telling, is because it's based on the real observation that you can tell where the sun is going to be, what constellation the sun is going to be in on the same day of the year every year. Well, then they took it too far, right? Because this is true, right? Astrology is true up to that point. It's when you start trying to do fortune telling to talk about people's future or people's personality or, very specific things that astrology tries to predict or explain, is where things go a little off the rails. But astrology is nonsense. It's not a science, but it is based in this real observation. And so if you're looking up your birth sign, right? If you're looking up your horoscope and you look up your birth sign is based on your birthday, right? Because on the same day of the year, everybody that's born on the same day of the year, the sun is in the same constellation. And that's why these astrological signs are the same, or are at least very close to the names of the constellations, right? Instead of Scorpius, the constellation is Scorpius, the sign is Scorpio, right? Sagittarius, Capricornus, Aquarius, Pisces, etc., right? They change things a little bit, but it's based on that observation, right? Doesn't matter what year you're born, everybody born on the same day, the Earth is in the same position in its orbit, and therefore the sun is in that same constellation. And so the whole basis of Western astrology is that your sign is the constellation that the sun is in on your birthday. Except there's a few problems here, right? Because astrology was invented over 2,000 years ago, it's 2,000 years out of date. And things have shifted a little bit over the last 2,000 years. So that's one of the problems. Why is that a problem? We'll see that in a second. One of the other problems in astrology is that there's only 12 birth signs, but there's actually 13 constellations that the sun goes through over the course of 1 year. There are 13 constellations in the zodiac, in the ecliptic. The 13th constellation is Ophiuchus. Ophiuchus is in between Scorpius and Sagittarius. And you can kind of understand, if I go back here, right? Ophiuchus is up over here. Ophiuchus is a big constellation, but the sun only crosses through a little corner of Ophiuchus over here. So the sun is only in Ophiuchus for a couple of weeks. So that's kind of understandable, but you're totally ignoring a whole constellation that the sun is in. All right. Kind of rude. When I say that the zodiac and the astrology is 2,000 years out of date, though, here's what I mean. I pulled this from a horoscope website. So here is, you're supposed to look up with your birthday what sign you are, what astrological sign you are. Okay, so look up your birthday. What sign are you? Okay, got it? Got your sign? Okay. So supposedly, astrology is based on between these dates, the sun is in Cancer, and that's what makes you a Cancer, for example. All right. So, unfortunately, these dates are based on where the sun was, what constellation the sun was in when astrology was invented 2,000 years ago. Ignoring Ophiuchus, so we're totally not accounting for Ophiuchus, that's going to throw everything off. That's not helpful. But more to the point, here's where the sun is now. These are the dates these are the dates when the sun is in these constellations in the modern day, in the current epoch. Has yours changed? Or has yours stayed the same? Most of you, for most of you, that constellation will have changed. If you take a large sample of people, it's about 81%. 81% of the population, the sun's not in the same constellation anymore. The sun is in the next constellation. Let's see. If you were born in February, then, or no, sorry. Oh, sorry. There we go. If you were born in, let's say, early February, the sun was in the middle of Capricornus. Well, according to this, if you were born in early February, let's see, there it is, right? If you were born in early February, it's like, oh, the sun was in Aquarius 2,000 years ago, and now it's smack dab in the middle of Capricornus, for example. Yeah. So for about 81% of the population, the sun was in a different constellation. It was in the next constellation. The sun has shifted by one constellation, by almost one full constellation, over the last 2,000 years. And for the other 19% of the population, the sun is actually still in the same constellation on their birthday. So for most people, things have shifted. Okay, let's see what effect that has on our observations. So those 13 constellations that the sun goes in front of over the course of the year, those are called the zodiacal constellations, based on the zodiac, sort of the name coming from astrology. So we've kept some of the naming. And in this diagram, it's also ignoring Ophiuchus. So just, know that it's up there, being annoyed that we're ignoring it constantly. Let's look here. All right. If you're standing there, right, and you're facing away from the sun, your position on Earth is opposite the sun, looking this way, then what would you see? Well, if you're looking south and Taurus is high in the sky, it must be nighttime, right? It must be nighttime because your position on the Earth is opposite the sun and you're looking this way. These constellations are going to be up in the evening, in the nighttime, opposite the sun. These constellations over here are up in the daytime, behind the sun. On this day of the year, what constellation is the sun in? Well, if the Earth is here, then right on this day, the sun is in Scorpius, right? What time is it, though? Well, we can use the motion of the stars to tell time, right? If you're standing right there and Taurus is opposite the sun, high in the southern sky, what time is it? Well, it must be midnight, right? Because your position on the Earth is facing directly away from the sun, so it must be midnight. If your position on the Earth is facing right toward the sun, then it would be noon, right? What are the constellations that appear on the eastern and western horizons? Well, if you're facing south, then east is on your left and west is on your right, which means we can figure out where the horizon is for you in this diagram too. We could say, all right, here's the half of the horizon here's the half of the sky above your horizon right now, right? There you are. Taurus is up over here. Cancer is on the eastern horizon. Pisces is on the western horizon. So remember, the horizon is just an imaginary plane perpendicular to wherever you're standing. So this half of the sky is above your horizon right now. This half of the sky is below your horizon at midnight. 12 hours later, well, 12 hours is half a rotation of the Earth. So if the Earth does half a rotation, then instead of facing this way, now you'll be facing this way. So now, 12 hours later, now what will be high in the sky, high in the south? Well, the Sun and Scorpius will. Because what time was it before? In this diagram, it's midnight. 12 hours later, it's noon. So of course you're going to be facing toward the Sun in Scorpius. Of course the Sun in Scorpius is going to be high in the sky, high in the southern sky. It's noon. The Sun is highest in the sky at noon. 18 hours later, all right, if we start this at midnight facing toward Taurus, 12 hours have passed, and now we're facing toward Scorpius. 18 hours have passed. Now Aquarius, right? Now instead of facing this way, the Earth is rotated. Now you're facing toward Aquarius. So now Aquarius will be high in the southern sky at, let's see, we started at midnight. 18 hours later, it's going to be 6 p.m. So Aquarius will be high in the southern sky at 6 p.m. that day. Where will Scorpius be? Well, Scorpius is behind the Sun, so Scorpius and the Sun will both be high in the southern sky at noon. What about 18 hours later? Go back to that question, right? 18 hours later, we started facing Taurus, then we're facing Scorpius, now we're facing Aquarius. The Earth hasn't moved that much. We've only let 18 hours pass, so the Earth hasn't moved that much over just 18 hours. The Earth is in the same place. The Sun is in front of Scorpius. Aquarius is going to be high in the southern sky. Where will the Sun be? Well, what did we say? It's 6 p.m., right? If it's 6 p.m., the Sun is going to be setting in the west, and Scorpius will be behind the Sun, setting in the west, because it's 6 p.m. How about 2 months later? Well, if it takes the Earth 12 months to go around the Sun, then only 2 months later, now let's see, the Earth will be right about there, right? 2 months later, the Earth is right about there, and now Cancer is opposite the Sun, so Cancer will be high in the southern sky at midnight. And what will be high in the southern sky at noon? Well, the Sun, because the Sun is always high in the southern sky at noon. And Capricornus will be behind the Sun, high in the south at noon, 2 months later. There it goes. Okay. So 2 months later, let's see, if 2 months later the Earth is right there, right? Then what will the sign be of a person born that day, right? If the Earth is there, then the Sun will be there. The Sun will be in front of Capricornus. So what sign will a person be if they're born on that day? Who cares? Astrology's nonsense. Okay. The Earth is also doing a third motion, right? The Earth spins. I got a little YouTube video here. Let's fast forward to the part we actually want. Okay. So here is the Earth's rotation axis, right? Here's the North Pole. Here's the South Pole. Here's the equator, the celestial equator out there, right? The Earth spins once a day. The Earth orbits around the Sun once a year, and the Earth also wobbles around. So what do I mean? The Earth doesn't just spin like a top. The Earth also wobbles like a top. And here we go. Here's what I want. Like this, right? The Earth wobbles like a top, but slowly, right? One wobble of the Earth takes 26,000 years. And so what does that mean? It means that right now, well, thereabouts in the year 2000, right? Right now, let's go back. There we go. Okay. So right now, the North Pole is pointing at Polaris, right? That's what makes Polaris the North Star, is that it's the star that lines up with the North Celestial Pole, right? It's the star that just so happens to be right above the Earth's North Pole. Except that over thousands of years, the North Pole wobbles. It wobbles as the Earth wobbles. And so the stars are slightly shifting from our point of view, right? As the Earth wobbles, then where stars appear to be and what day of the year they appear, slowly shifts, slowly wobbles around with it. Okay? So, in other words, from the Earth's point of view, right? Here's the North Celestial Pole, right? 2,000 years ago, the North Pole was pointing over here. Now, it's pointing here at Polaris, right? The tail of Ursa Minor, the last star in the Little Dipper, right? And it's going to keep on going. When I said astrology is 2,000 years out of date, this is what I meant, is that over the last 2,000 years, from here, from here to here, the North Pole, the alignment of the Earth has shifted a little over. And since the Earth has shifted a little bit, then from our point of view, it looks like the stars have shifted a little bit. And that's why the sun isn't in front of the same constellations on the same day of the year anymore. At least not for most of us, right? The sun hasn't moved, the star hasn't moved. It's just the Earth that has wobbled a little bit around. As I said, one full wobble takes 26,000 years. So over just 2,000 years, the Earth has shifted enough so that for 81% of the population, the sun isn't in the same constellation on your birthday as it was 2,000 years ago. And the Earth is going to keep on wobbling, right? This is kind of cool. If you go to the Hoover Dam, right? If you go to the Hoover Dam, outside of the visitor center, there's the statues, and it looks very cool. And if you look down at the ground, there's this metal and marble inlaid pattern on the ground. And if you read all of this text, it explains to you what you're looking at. But let me give you the short version here. Each of these circles is a star. And here's the Little Dipper, right? There's Polaris. And if you zoom in, what you see is there's Polaris, and there's where the North Celestial Pole was pointing on the day the Hoover Dam opened in 1930, I think it was 1936, right? This yellow circle is the path of the North Celestial Pole. It's the path that the North Celestial Pole takes around the stars once every 26,000 years as the Earth wobbles around. And so this is a calendar. It's basically, it says the Hoover Dam opened in 1936 when the North Celestial Pole was here and Polaris was over here. And since 1936, the North Celestial Pole has actually gotten closer to Polaris. It's about here right now. Right? Here's where it was in 1936. Here's where it is today. The North Celestial Pole is going to get closer and closer and closer over the next few decades until right about here. The North Celestial Pole is going to get as close as it can get to Polaris in the year 2100, and then after the year 2100, it's going to start wobbling away. We only have a North Star today because there's a bright star close to the North Celestial Pole. And since 1936, it's gotten closer and closer and closer. It's going to get closest in the year 2100. And then starting in the year 2100, the North Celestial Pole is going to keep on wobbling further and further away. And then in another 1,000 years, there won't be a North Star. Right? 1,000 years from now, the North Pole will be over here, and there won't be another star lined up with the North Pole. Polaris will still be there. Polaris will be just another northern star near the North Pole, but it won't be the North Star anymore. Right? For most of history, there wasn't a North Star. Right? 2,000 years ago, the North Pole was over here. And there were all these stars. There are all of these, the Little Dipper, the stars of Draco over here. 2,000 years ago, the North Pole was over here, and there was just a bunch of stars near the North Pole. Today, there's a North Star. There's one other little thing in this map that I think is really cool. If you look over here, 5,000 years ago, the North Pole was over here. And there was a North Star 5,000 years ago, but it wasn't Polaris. It was the star Thuban in the constellation Draco. And when you look, and the reason why they put the pyramids in this map is that 5,000 years ago is when the ancient Egyptians were building the Great Pyramids on the Giza Plateau. And one of the amazing things about the Giza pyramids is that they're lined up with north, south, east, and west. They built the pyramids 5,000 years ago. They built the pyramids lined up with true north. How did they do it? Well, they had the North Star to guide them. But it wasn't Polaris, it was Thuban. Right? There was a North Star 5,000 years ago. Then there wasn't a North Star for the better part of 5,000 years. And now, for the last few hundred years, we've had the North Star again. And we're gonna have Polaris as a North Star for the next few hundred years, and then eventually the Earth is gonna keep on wobbling, and we won't have another one for a long, long time. It is completely a coincidence that we just so happen to have a North Star right now. And like I said a minute ago, there is no South Star. There's a bunch of stars near the South Celestial Pole, but there isn't one lined up with the South Celestial Pole like Polaris is with the North Pole. All right? So, what are we taking from this? Well, let's go back here. Let's go here, right? So, the Earth is doing three kinds of motion. It rotates once a day, it revolves around the sun once a year, and it wobbles on its axis. It precesses once every 26,000 years. And all three of these motions change our view of the sky, but the thing that makes it easy is they're happening at very different speeds, right? The Earth spins once a day, orbits once a year, wobbles every 20,000 years. it's easy for us to figure out why the sky is moving the way it is because they're happening at such different speeds over such different time scales, right? If you're interested in how the sky moves over the course of one night, all you need to care about is the Earth rotating. Because the Earth is rotating the Earth is rotating through a lot of its rotation over the course of one night, but the Earth is not moving around the sun or wobbling much in just one night. The rotation of the Earth is the only thing that matters. If you're interested in how the sky changes month after month, season after season, then you got to take the Earth's orbit around the sun into consideration and figure out what constellation the sun is in front of. And if you're thinking about how the sky changes over the course of thousands and thousands of years, then you've got to do like they did here and... Come on. Well, you got to do like they did here and... Come on. Gonna be giving me trouble. Okay. And predict, where was the North Celestial Pole 1,000 years ago, 2,000 years ago, 5,000 years ago. And once you know where the North Pole was aligned, either thousands of years in the past or thousands of years in the future, then you can say, well, if the North Pole is here, the rest of the sky would have been in these positions, at these right ascensions and declinations. And then you can tell where everything is. And so if you're interested in archaeology, then this is a cool piece of ancient astronomy to say, how was the sky different for the ancient Romans, the ancient Egyptians, the ancient Anasazi, or the ancient Chinese, or, different people throughout history have seen the sky slightly different because the Earth shifted just a little bit over thousands of years. Okay. So, that's a lot. We've gone through a lot today. But that's going to help us unpack all of this for the next 3 tools in the microtask book. So, we'll work on tools 3 through 5 in the book, and the next assignment in Taurus is called coordinate systems. So, go ahead and work on the Coordinate Systems Taurus book. It will talk about all of these things, and you'll get a little more practice with all of these, and we'll get some more practice also in the book. Okay? Have a good day, everybody.